Hello and welcome to the third part of lesson number 2 in Unit 6, Solving Problems with Quadratics in our grade 10 academic math class. So this is optimization problems part 1, so the first day of this. We've done 2 examples so far, worked our way through, sort of a general one involving numbers, a second example that involves area of a rectangle, and our third example is more similar to the second example than the first. It just layers in a little bit of extra work for us. So let's just jump in. Again, if you want to pause here and sort of copy out the information that I put on the page, it might be helpful moving on. I'm going to assume that you already have it written down, so if you're following along, having it written down might just be really helpful. So take a second, copy it down, then come on back and we'll move through this. Okay, example 3. A rectangular field beside a river is to be fenced on 3 sides. Find the dimensions that produce the maximum area if $180 can be spent and the fencing costs $2.25 per meter. Okay. So this question, actually very similar to the last question, it just involves a little bit of front-end work. So again, as I read this, I see the words maximum and area. Maximum, of course, tells me that I'm going to be looking for a vertex and that I'm working with a quadratic. Area just reinforces that, since that I know that the area formula, length times width, is a second degree equation, which is a quadratic. So the little twist at the beginning of this one is that it doesn't explicitly tell you what the perimeter of fence you have to play with is going to be. We need to figure that out. So we know that we have $180 that we can spend on the fencing, and that every 1 meter of fencing costs $2.25. So how many meters of fencing can we buy with $180? Well, if we take our $180 and divide it up into $2.25 chunks, we can figure that out. So we put into our calculator $180 and we divide that by $2.25. That's going to give us 80. So we divide this by the $2.25 that we know it costs per meter, and that will give us 80 meters of fencing to play with. 80 meters of fencing that will make up the 3 sides. So that's just a little introductory calculation, just to kind of throw a bit of a curveball at you so you don't get just into this routine of just like go and go and go and go. This one requires a little bit of thinking. So once we know that we've got 80 meters of fencing to make up all 3 sides of our fenced field, we can now start to, of course, define our variables, which I hope you've already copied out. Very similar to the question before. We have perimeter, length, width, all measured in meters, and we have area in square meters. So let's start building some equations here. The first equation that we know is going to be that perimeter equation. Now, again, the bit of a twist on this one is that we're talking about a 3-side, whoops, I want the highlighter. It's a 3-sided shape that we're building here. So, or I guess a 3-sided enclosure. So we know that our perimeter formula is going to be a little bit different this time. So let's have a look at that. Let's call that number 1. So number 1 is for perimeter. This time it's going to be 2 widths and only 1 length, because that second length is actually the river and we don't need it this time. If we go on, we recall that our perimeter was going to be 80. We had 2 W's and 1 length. So there is our first equation. The second equation, as before, because we're shooting for a maximum area, we're going to be using the area formula. And the area formula, of course, is length times width. So we have our linear, and again, recall that this is a linear equation because it is a degree 1 and a degree 1. So those are separate, so it's a degree 1 equation. This one down here, however, this is degree 2, since collectively, and I say collectively because these 2 terms are being multiplied together, which would result in us, if we were to be able to combine them, we would be adding our exponents together. So this is degree 2. So we are going to start by substituting a version of 1, the linear, into 2. So let's start by rearranging here. We are going to rearrange 1. So I'm going to isolate L, makes the most sense because it's just kind of sitting there all by itself. So we have L is going to be equal to 80 minus 2 W's, and we're going to call that number 3. All right, so the next thing we're going to do here is we are going to substitute 3 into 2. 3 into 2. Okie doke. Let's do that. So we have the area is equal to, now in the place of length, this time we have 80 minus 2w, and then we have our original w hanging around out there. So we are going to expand this out into our quadratic now. Let's make that happen. So that's 80 times w and negative 2w times w. So that's going to give us a equals 80w minus 2w squared. Let's reorganize this into an order by degrees. And here we have our quadratic. Again, no c value, that's okay. So maximum, all the way back at the beginning, maximum was our clue that we are going to be completing the square. Oh, we got lots of space this time. I guess I'll just keep working vertically here. So we are going to complete the square. Complete the square. And we start our completing of the square by common factoring out negative 2. Because we need to start with a perfect square when we're building our perfect square trinomial. So there we go. We have negative 2. We factored that out of negative 2w squared. Leaves us with w squared. Factor negative 2 out of 80 gives us negative 40w. Now we are going to add something. And we are going to take something away. And that is going to help us complete the square. So again, how do we do that? Well, we're looking at our b value. We're going to take half of our b value, which in this case is going to be negative 20, and then we're going to square that, which is going to give us 400. So let's put 400 on the board. We're going to add it, and then we're going to subtract it. And again, I know I say this every time. This one we put in to create our perfect square trinomial. This one we put in to keep our equation balanced. So let's free that negative 400 from our equation by multiplying it by negative 2. So let's see what our next line is going to look like here. Next line, area equals negative 2 bracket w squared minus 40w plus 400, close the bracket, and that's going to be plus 800 out here. Okay, and now we factor. So area equals, that negative 2 hangs around. Now here inside these brackets, we know it's going to start with a w. We know that the sign inside the bracket will be negative since our b value is negative. What multiplies to negative 400 but adds to negative 40 is going to be 20. And there is our plus 800 hanging out on the outside there. So let's interpret our solution here. So our vertex is going to be 20 and 800. Again, and I know I sort of say this every time, but this was our input value. There's our output value. So 20 is going to correspond to W. So the width of our rectangular three-sided enclosure is going to be 20. And our maximum area, our output value, is going to be 800 square meters. So we still need to figure out, however, what our other variable is. So let's, I guess we're kind of out of space in this row. So let's just go start on the other side. So we want to now find L. And we're going to find L by substituting into the rearranged number 1. So that was 80 minus 2W's. So L will then be equal to 80 minus 2 times, rather 2 times 20, sorry. And then our length will be equal to 80 minus 40, or length equal to 40. So there we have our two values. Now we just got to sum it up. Therefore, the dimensions of the enclosure are 20 meters by 40 meters. And there is our therefore statement. So again, just to recap what we did here, this one had a little bit of a twist at the beginning in that we needed to find exactly how much perimeter we were working with. After we found that 80 meters, we created our two equations based on the question. So we developed a perimeter equation, which was our linear equation, and we developed our area equation, which is our quadratic. We rearranged one to substitute it into the second quadratic equation, and then we expanded out and simplified, giving us negative 2w squared plus 80w. We then completed the square to give us 20 and 800, which we interpreted as being a width of 20 meters and a maximum area of 800. We sub back into find L into our linear equation, gives us 40, and then we write ourselves a little therefore statement. So there it is. That's our third and final example for this lesson. Now there are a few questions lined up here on the optimization problem worksheet and a few questions from your textbook. I fully expect there to be lots of questions in this unit and in this lesson and all the lessons, so throw me emails, ask me questions. I'll provide clarity when I can. Obviously the filled out versions of these notes are also up on our class website, so if you just kind of need to get a peek at where we were going, that's fine. If you're just sort of struggling and want some advice and really want to figure it out on your own, by all means email, let me know what's going on and how I can help. Hopefully the homework goes well, and we'll see you in lesson number 3, which is optimization part 2, so more of the same.